I hope I am audible. Good evening, everyone. Welcome to the week 7 live interaction session for the course on Renewable Energy Engineering, Solar, Wind, and Biomass Energy System. Let's just wait for a few minutes for others to join before we begin our session for today. Let's just start our session for today. Let me present my screen. I hope I am audible. Can anybody? Yeah. Thank you so much. Let just let me present my entire screen. I hope my presentation is visible. Yeah, okay. Now I hope it is visible even in the presentation mode. So yeah, let's just start our session for today. I welcome you all to the week 7 live interaction session for the course on renewable energy engineering, solar, wind and biomass energy system. I am Pratyumnan, currently a PhD scholar at the Department of Chemical Engineering, Indian Institute of Technology. I am the course team member who is responsible for conducting the live interaction session every week. This course is offered by Professor Vaibhav Vishant Gaud sir and Professor Anandalakshmi ma'am from the Department of Chemical Engineering, IIT Guwahati, Assam under the NPTEL program. So we have come up for like 6 weeks of the live interaction session has been completed, and we completed one big topic of solar energy, and then we have moved on to something called as biomass energy systems. So last week we dedicated our interest towards understanding how biomass is a energy resource, and how solar energy is indirectly being used even in this biomass energy system through photosynthesis. And then we saw about the structure of the biomass, the various components present in the biomass, and we also saw how to characterize the biomass using two different thermal techniques like TGA and DTG. So TGA is nothing but thermogravimetric analysis method, which you use to identify how does your material is going to degrade under different temperature condition. And through your one more is the DTG method, through it's a differential thermal gravimetric method, through which you will be able to understand if there are two similar components that is undergoing a degradation at similar temperature. Through the DTG plot you will be able to understand how much amount of the degradation is happening for one particular component compared to the other one. So till last week we saw about what is actually a biomass is, its properties. In this week, week 7 session, we will be focusing on how do we use this biomass for our beneficiary purposes. How do we convert the biomass into energy so that we can ultimately enjoy using this energy, which is pollution free and without any use of fossil fuels. We will focus on this aspect for this session. So before moving on towards the week 7 session, let's just see some of the formulas that we used for analyzing the biomass samples. So the first, so here are a list of approximately 6 different formulas. You have your moisture content. It's specifically focused on your proximate analysis. So you in your proximate analysis you have your moisture content, you have your LHV, that is called lower heating value, you have your HHV, that is called higher heating value. How to determine the percentage of ash, how do you determine the percentage of fixed carbon in case of the dry basis as well as the wet basis. As we discussed in the previous lecture as well, when you in case of the biomass sample, on what basis are you asked to solve the problem is very important. If suppose if the basis is a wet basis, then you have to take your entire solving strategy on the basis of the weight of the wet sample. If it is asked on the dry basis, then your entire strategy towards solving the problem should be on the dry by using the dry samples weight. For example, if you see the formulas 2 as well as 3, the moisture content on dry basis and wet basis, it is similar. In both these places you are actually going to determine the moisture content, but the basis becomes different, so that your denominator if you see is also different. In case of dry basis, you divide your moisture content with the weight of dry sample, whereas in case of your wet basis you divide the moisture content with the weight of the wet biomass sample. So this is the difference, and this is a very crucial difference that exists in the biomass, where you have to be careful on what basis you are asked to solve the problem. So here we have few terms. We have discussed these terms even in the previous week, and we have solved problems on the basis of these terms, but still I just would like you to answer about what you actually mean by the percentage of fixed carbon. What do you mean by, like, why is there is a specific term fixed as a prefix to the carbon? So just because something is fixed carbon is written, so does that mean there is something also called non-fixed carbon present in your biomass sample? So I would like to know how many of you actually know what is the meaning of percentage fixed carbon. Like, what is the meaning of the fixed carbon? Anyone? Yes. We have solved problems based on these two formulas last week also, on how to determine the percentage of the fixed carbon in your biomass sample. If you remember, let me just go back to that problem. Yes, this is the week 6 session, the PowerPoint presentation for week 6 session. So here if you see the fourth problem, we have discussed about the percentage of fixed carbon in the biomass sample, its calculation, where we were asked to find the percentage of the fixed carbon of a biomass sample on wet as well as the dry basis. So we have solved the problem. We identified the moisture percentage present in the biomass sample using this formula, where let me just zoom in, where we know the weight of the crucible and we know the weight of the biomass plus crucible, we know the moisture content that is present in the sample, and then we calculated the percentage of moisture. So with this formula, percentage of fixed carbon in dry basis as 100 minus volatile plus ash, and wet basis you have a moisture term added in excess to that, and then we calculated the fixed carbon dry basis as 68.75 and wet basis as 63.28 percentage as such. And if I am not wrong, you also had a problem in the week 6 assignment where you were asked to find the percentage of the fixed carbon. But what is actually the meaning of the percentage of fixed carbon? What does the term actually means? Somebody? So your percentage of fixed carbon is nothing but the non-volatile carbon content present in your sample. So if you remember the TGA plot that we saw last week, there was something called as a volatile matter which will get readily evaporated when you increase the temperature. So there is something called volatile carbon and there is something called fixed carbon. Volatile carbons are the ones that actually gets converted to CO2 or gets volatilized when you increase the temperature. But fixed carbon is something that remains in your biomass sample even after you increase the temperature to a larger extent. Like even if you increase your temperature, even if you increase your temperature to a very high amount, the carbon that remains in your sample without getting volatilized is nothing but is the percentage of fixed carbon in your sample. So let me just repeat the definition again. It is the portion of the sample or the non-volatile carbon present in the sample as residue even after the volatile matter is removed. So the non-volatile carbon, let me just write it here. What is fixed carbon? Fixed carbon is nothing but your non-volatile carbon which remains in your sample even at a high temperature as residue. So here we have seen the formulas. So these are the 6 important formulas that you will require while doing the proximate analysis for the biomass. But if you remember, last time when we talked about the characterization of the biomass sample, we talked about another kind of analysis which is nothing but the ultimate analysis of the biomass. So in case of the proximate analysis, you just have your all the physical properties comes into picture in case of your proximate analysis, that is your volatile matter, percentage of fixed carbon, moisture as well as the ash. So these are and the density of the sample also we have discussed. So these physical properties or the physical nature of your biomass sample is something which comes under your proximate analysis. But what do you actually want to know is the chemical structure or the chemical composition of your sample. So if you have to do those, then you have to do your ultimate analysis, which is nothing but over there you will be able to determine your percentage of elemental composition present in the sample, such as percentage of your carbon, percentage of your oxygen, percentage of your hydrogen, sulfur, nitrogen and other kind of mineral matter if it is present. So if you see here, these are 2 pie charts. So these are for a specific biomass sample. They have done the proximate as well as the ultimate analysis, and they have reported what is the percentage of each of the element in that biomass sample. Similarly, in case of your proximate analysis as well. So in order to do this ultimate analysis, like proximate analysis, we went with the TGA and DTG, where we were able to determine what is the moisture content, how much volatile percentage is present, what is the percentage of fixed carbon, how much ash is present. If you remember, or let me just show that week 6 presentation. Yeah, here. So once you start increasing your temperature of the biomass from the room temperature to a higher temperature, you will start the very first step of the decrease in the weight will determine your will be designated as the moisture content. Then the next weight decrease step will be assigned as a volatile matter that is present in your sample. Afterwards will be your fixed carbon, and at the end, when your mass becomes constant, even if you keep increasing the temperature, that particular portion will be designated for your ash percentage. So using your TGA plot, you will be able to do the proximate analysis of your sample. But if you have to do your ultimate analysis, that is finding out your elemental composition, then you have specific techniques which you have to follow to determine the percentage elemental composition of your biomass sample. So here we will discuss about totally 5 different percentage of the elements. One is your carbon, hydrogen, oxygen, sulfur and nitrogen. There may be other kind of elements also present, but they will be in trace quantities and they can be considered as impurities. So those quantities which will be present in the trace amount might be your inorganic constituent, which will come under the classification of ash. If you remember, the definition of the ash is something that it is a inorganic matter, non-combustible inorganic substances. So all those kind of trace amounts of inorganic components will be classified under the ash category of your proximate analysis. So here we will discuss only about these 5 elements and how to find them through various chemical techniques. So here you have the first one on how do you find the carbon as well as the hydrogen content of your biomass sample. So you take some amount of your biomass sample and then you actually burn it in the oxygen. So the CO, the carbon, when it is burnt in stoichiometric ratios of oxygen or excess supply of the oxygen, will get converted to carbon dioxide, and hydrogen will react with oxygen forming water molecules. Remember here the word stoichiometric is important, because if you react your carbon samples or the biomass sample with limited supply of oxygen, then it will result in an incomplete combustion forming CO, carbon monoxide. Only when the amount of oxygen supplied is in excess or is in the stoichiometric ratios, then only complete combustion will happen and your carbon will react with the sufficient amount of oxygen, resulting in the carbon dioxide production. So your carbon dioxide as well as H2O is released after burning the samples. This carbon dioxide is going to be absorbed by your KOH, and H2O is going to be absorbed by your CaCl2, calcium anhydrous. So CaCl2 is usually in anhydrous form, is hygroscopic in nature. So when the water is passed through the CaCl2, the water molecules will be absorbed by the calcium chloride. So once there is a absorption of the CO2 by KOH as well as H2O by CaCl2, there will be an increase in the weight of the so this KOH as well as CaCl2 will be actually stored in tubes. So once this CO2 passes through your KOH tube and H2O through a CaCl tube, the weight of the tube will increase. So depending upon the increase in the weight, we will determine the percentage of carbon as well as the hydrogen present in your biomass sample. So here are the two formulas on how do you determine the percentage of carbon. So increase in the weight of KOH tube into 12 into 100 divided by weight of biomass into 44. So these are just the formulas. So similarly for percentage of hydrogen, you multiply that with increase in the weight of CaCl tube into 2 divided by weight of biomass into 18. But you need to understand how did this formula actually come out. So let me just write this here. Let me move to another slide and then there I will write it here. So let me make another slide. So your carbon is going to react with O2, resulting in the formation of carbon dioxide. So the molecular weight of carbon is 12, that everybody knows, and your molecular weight of carbon dioxide is 12 plus oxygen will be 32, so that will be 44. So here, so this is the molar mass of carbon as well as the molar mass of carbon dioxide and atomic weight of carbon. So now your CO2 is going to be absorbed by your KOH. So the increase in the weight of your KOH tube will be nothing but because of the CO2 content. So let's assume that the increase in your KOH tube be X. The weight of increase in your KOH tube be X. Now for this much amount of CO2 that is actually generated, how much percentage of the carbon is present in the sample is what we have to identify. This simple 12th, probably if I am not wrong, it will be a 11th or a 12th grade problem. So let's just finish this. So now you want to find the carbon percent. So how will you find? Here you know the X because you can actually identify what is the percentage of weight increase in your KOH tube. So C will be nothing but X times 12 divided by 44. So this will be the amount of carbon, that is the carbon that will be present in your biomass, in your sample. So here we are just finding out how much carbon is going to be present. So for that we just divide it with your weight of biomass, and then in order to find the percentage we actually multiply that with 100. So increase in the weight of your KOH tube times 12 divided by 44 will give you the amount of carbon, and that divided by your weight of biomass into 100 will give you the percentage of carbon that is present in your biomass sample in terms of percentage. Similarly, it is for the percentage of hydrogen also. So H2 plus half O2 gives you H2O. So H2's molecular weight is 2, H2O's weight will be 18, and you know how much amount of your water is going to get absorbed by your CaCl2. So that increase in your weight of that particular tube, and let me just show that also. So H2 plus 0.5 O2 will give your H2O. So the molecular weight is 2, and here for H2O molecular weight is 18, and you know how much amount of the weight is going to be increased in your CaCl tube due to the absorption of water molecules by your calcium chloride. So let that be X. X is known to us. here we need to calculate how much hydrogen is going to be present, how much hydrogen is going to be present in the sample or in the biomass sample. So that will be nothing but H will be equal to 2 times x, that is your increase in the weight of the CaCl tube, by 80. And to find out that in the biomass sample, you divide it by weight of biomass and multiply that by 100 to find the percentage of the hydrogen content in your sample. Similarly, we move for nitrogen content, sulfur content and ash content. So in nitrogen content, we do not use those kind of method what we use for carbon as well as that of the hydrogen. Here your percentage of the nitrogen content is determined by a method called Geldal method. So here what happens is, you take your biomass sample, you heat the biomass in the presence of H2SO4 acid as well as K2SO4. So the sulfate component, the nitrogen that is present in your sample, will react with them, forming your sulfate component. This sulfate component will then react with some kind of alkali solution like sodium hydroxide or potassium hydroxide, and then they will generate the ammonia. The ammonia is actually absorbed by some acids like HCl or boric acid and forms again ammonium sulfate. So whatever amount of the acid that is left out, the unused acid or the acid that did not form that did not react with your ammonia, is titrated against your sodium hydroxide solution, and with that you can actually get to know your percentage of nitrogen. So that is nothing but volume of acid into normality of acid into 1.4 divided by your weight of biomass. Similar is the percentage of sulfur content. So what you do is, you take your sulfur, burn the sulfur. So once you do, what happens is that after burning that sulfur, you wash that sulfur with some acidic solution to form the sulfur component of that particular, the sulfate component. Now you react that sulfate component with the barium chloride. So when a particular sulfate component will react with barium chloride, it will form barium sulfate. So similar to what you have seen in finding the percentage of carbon as well as the hydrogen, here you take BaSO4 and its molecular weight is 233 and sulfur molecular weight is 32. So it's just that you need to do the cross multiplication what we did previously in the while finding out the percentage of carbon and hydrogen, then you get your percentage of sulfur, and then you move on towards your finding out the ash content. So this we have discussed the last week in week 6 lecture also. We solved a problem. I guess it's the next problem. Yeah, here we were asked to calculate the percentage of ash. So that is nothing but, you take your biomass sample again. Here you heat the sample to a very high temperature, let the mass becomes constant. So once the mass become constant, you take that residue out and then cool the residue and then weigh it. Whatever the weight you obtain after cooling it down is nothing but weight of your ash, and you know your weight of the biomass sample that you had taken initially before you start heating the biomass sample. So what is left at the end is nothing but your ash, and you know your weight of the biomass, what is there, what you started burning it previously, like weight of the biomass initially before burning, and that into 100 will be your percentage of the ash that is present in the biomass sample. Here you use muffle furnace, because using the muffle furnace we will be able to reach up to a very high temperatures of beyond 1000 degrees Celsius. So with that you will be able to calculate the amount of ash that will be present as residue after you burn the biomass sample. So this is the ultimate analysis, and for finding the percentage of oxygen, we do not have a specific method like how you do it in the case of carbon and hydrogen or your nitrogen, such as that Jaldal method. So here what you know is, you know the percentage of carbon, hydrogen, sulfur and nitrogen, and yeah, so these will be the major constituent. So if you subtract 100 from them, or if you if you subtract all these combinations from 100, that will be whatever the difference that is going to be left out is nothing but something that will be assigned to your percentage of oxygen. So percentage of oxygen will be nothing but 100 minus of percentage of carbon, hydrogen, sulfur as well as the nitrogen that is present in your biomass sample. So so let me just ask if in case anyone has any doubts related to this. Do you have any kind of doubt? Because this is something that is not covered in the video lecture. So ultimate analysis part is something what we are covering now as an addition, because this will complete the characterization of the biomass as a whole. So it's not just that we have to deal with the proximate analysis, but also we have to understand about how to calculate the elemental percentages in your biomass sample. So if you have any doubt, then please do let me know. So if in case nobody has any doubt, then we can move on to the next topic. So the thing is, we have done the ultimate analysis and we know that it is important to find the elemental composition. But how does this elemental composition, like we get some particular information by knowing the elemental composition of our biomass sample, but how will it be helpful from energy perspective? Like I'm going to find the elemental composition of some sample, but why do I do that? I mean, by doing that, what am I going to get? Is there some specific information that I'll be able to take up, or that I'll be able to extract out, or is it something just to find out the formula of my biomass sample? So let us now look at that, on why do we do the ultimate analysis of our biomass sample. So the question is, but why ultimate analysis is done? So the answer is that the percentage of elemental composition that is present in your biomass sample actually affects the calorific value of your biomass as a fuel. So if you have any idea about calorific value, like can you just tell me what do you actually understand by the term calorific value? Yes, this is something that we keep repeating. This word keeps getting repeated in whenever we deal with biomass or any kind of energy related topics. They use this word calorific value. So what is actually, like, what understanding do we have when we speak the word, or when we put up the word calorific value of a fuel? So it's just very simple. Calorific value is nothing but what is the total energy that gets produced in the form of heat when you combust the substance, when you burn your substance, or when you burn your biomass sample. how much amount of energy is going to be released out of it as heat, how much amount of energy will I be able to harness out when I burn my biomass sample. So that is what is not called as your defined as the calorific value of any particular fuel, not just as a biomass. How much amount of energy in the form of the heat will be released when the substance is combust completely in oxygen under standard conditions. So this is the exact definition. In a more simpler terms, what will be the amount of energy that I will be able to gain when I combust or like burn my sample in air. So that is what is called as the calorific value. So this term is important here because the amount of elements that is present in our biomass sample will affect the calorific value of our biomass as a fuel when it is used in some applications. So how does it going to affect, or what are the elements are going to affect our calorific value? That's what we will be discussing now. So here we have, so since we have discussed about carbon, hydrogen, oxygen, sulfur and nitrogen and ash content, so we will be taking up with that and then really understand why something will add to the calorific value, or how do I, or what is the better characteristic of a biomass sample. Let's say if I have two biomass sample, let's say if I know the percentage of the elements in my biomass sample, with the understanding of this percentage elemental composition present in my biomass, how will I be able to differentiate the two, which one among the two biomass sample is a better fuel, or which will help me in harnessing more amount of energy with a limited quantity. So that's what is we will be discussing now. So greater is your carbon as well as the hydrogen that will add to your calorific value of the fuel. So the carbon as well as the hydrogen are the main characteristic for your biomass sample. Higher the percentage of carbon and hydrogen present in your sample, better will be the calorific value of your fuel that you are going to use. But one of the thing with the hydrogen is what happens is majority of the hydrogen actually readily gets volatilized, or actually moves out when you moves out as volatile matter. So that is one of the kind of, like you can say, a limitation. But if the carbon percentage is more, then it is a sure shot that that particular fuel will be having a high calorific value. Whereas if you see in case of your nitrogen, the nitrogen does not contribute to your calorific value. The reason is that the nitrogen is a non-combustible gas. So your N2, so nitrogen is nitrogen will not be able to the calorific values because they are non-combustible. They cannot actually burn and then release the heat, unlike in case of carbon, which will burn and then get converted to CO or CO2 and then release the heat. In case of nitrogen, it is not possible because of their tight bonding that exists in their molecules. So due to this, their contribution to calorific value will be low. If you see in case of the next is the sulfur content. Here your sulfur content will be adding to your calorific value, but there is a issue. When the sulfur actually reacts with oxygen, it forms oxides of sulfur such as SO2 and SO3. The problem with this SO2 and SO3, or some kind of an SOX, like let's say X is a kind of arbitrary number, because sulfur can actually react with oxygen forming different kinds of oxides. So when the sulfur and the oxygen reacts and forms oxides of sulfur, these oxides of the sulfur has the potential to create harm to the environment. So the SO2 as well as the SO3 or other kinds of oxides of the sulfur, when they are released to the environment, it will be very harmful for the human beings. So if you know, then it's the nitrogen NOx as well as the oxides of nitrogen and oxides of sulfur is something that what contributes to the acid rain formation. uh, I hope you have a understanding of that. So when the sulfur oxides or oxides of the sulfur, when they are generated, they are exposed to the atmosphere. Since it's a gas, they will rise up in the atmosphere and then move up to the top. There, when they come in contact with the water molecules, so the H2O as well as this SO, the oxides of the sulfur, when they react with when they both react together, it forms sulfuric acid. So this sulfuric acid what gets precipitated out as rain. So that is the reason why we say that the oxides of sulfur pollutes the environment. It's not just that they mix up with the atmospheric air and create harm to the human beings, but also they rise up in the atmosphere, react with the water molecules present there, forming sulfuric acid and gets precipitated down in the ground. So that is one of the reasons why the sulfur content, even though it adds calorific value to our fuel, the percentage of the sulfur content should be low because it will harm our environment. So when we take a biomass sample, it should be in our we should be conscious about the percentage of the sulfur content, that the content of sulfur in your what fuel you are going to select should be low. Then if you come to your oxygen content, so the presence of the oxygen in your biomass or in your fuel will reduce the calorific value of the fuel. There is a main reason why this is the case, because when the oxygen content is more in a particular fuel, it is inherently meant that this high percentage of the oxygen is due to the high moisture content present in my sample. So high moisture content means water content will be more. So if the water content will be more, then so much amount of the heat has to be given to the biomass sample in order to start burning. Because if you take a wet biomass and if you start heating that, it will take a long time, because first once you start heating, the water vapors that are present as the moisture content, the water that is present as the moisture content should get evaporated, then only the burning will start. So much amount of the heat will be given in to the system in order to start its ignition itself if the water content is more. This is the reason why the oxygen content should be low, because the presence of the oxygen content in your sample is inherently considered as your moisture content, and presence of the moisture content will kind of hinder the temperature at which your ignition start, or how much amount of the energy that has to be given in for the ignition to start. And that's why this should be low. And one more reason is because if the oxygen is present, the hydrogen that is present in the sample might react with both of them and then form water molecules. That is what I said as moisture. Oxygen might react with your hydrogen, resulting in the formation of water molecules, and that water molecules will lower down your calorific value. The major reason, as we said before, because much amount of the heat has to be given in order to start the ignition of your biomass sample. After that, we come to your ash content. Ash content is nothing but is as I said previously, it is nothing but your inorganic constituent present in your biomass sample. So the inorganic constituent, in order to make them combustible, the temperature that you have to achieve will be very high. So that may not be possible with the temperatures or with the equipments that we use now. Like probably the inorganic substances will be combustible beyond 1500 or 2000 degrees Celsius, whereas if you see your biomass, all those things, their entire combustion process will get over by 800 degrees Celsius, which is much lesser compared to your inorganic constituents. So that's why we call them ash content as non-combustible, because you require a very high temperature for them to start to start their combustion. So this also will reduce the calorific value of your biomass as a fuel. So if we take two biomass, let's say biomass A and biomass B, if you suppose someone is going to give you these two, and then let's say that they have given the characteristics, both they have done the proximate analysis of biomass A and biomass B, similarly the ultimate analysis of both the biomass, then they are going to ask you to choose which one you will take as a fuel for any of your application that you want. Then these will be certain details that you will have to check before choosing which fuel will be the best one for you. So in the modern days, we use CHNS analyzer. It's an instrument which will determine your percentage of carbon, hydrogen, nitrogen as well as the sulfur present in the sample. So here we have a question, but before that let me know in case if you have any doubts. If you have any doubts, then please let me know, like based on what we have discussed in the last 45 minutes. Oh, okay, yeah, okay, yeah. Then so let's just move towards solving the problem. So here is the problem. Let me zoom in. Here we are asked to calculate the percentage of carbon, nitrogen, hydrogen, sulfur and oxygen in the sample using the following information. So you have like 4 different information. I'll just give you some time to really look through what will be your, like what are the information that is given, and then after like 1 or 2 minutes, let's start solving the problem. Meanwhile, even if you want, you guys can also, because you know the formulas, these are very straight formula based questions. In majority, in case of the biomass, if you see in the last 2 weeks, this week and the previous week, we are specifically dealing with problems which you can solve very easily if you use the formulas. From next week onwards, we might be solving questions which are quite formula based. At the same time, they will be more towards designing of your biogas plant. So for this week, these are just formula based problems. So they have given you 4 different information. The first information says that they burn your 1.8 gram of some sample biomass A. Let just that be any biomass sample. It's going to get burnt, and then you observe an increase in the weight of your anhydrous CaCl2 and the KOH that is going to be present in your tube. And your next information is again some amount of your biomass sample of the same sample A you are going to take, burn that in a bomb calorimeter. So bomb calorimeter is a kind of instrument which will be used to evaluate or measure your calorific value of your biomass sample. So you take your biomass sample and then you combust it or burn it using high pressure oxygen in a metal pressure vessel. So you have a metal pressure vessel and you put your biomass sample and then you burn this under high pressure oxygen environment. So once it start burning, it will start releasing the heat. The energy that is getting released upon the burning will be absorbed by the water that will be surrounding this metal pressure vessel. So the rise in the temperature of your water will be directly proportional to the heat, will be considered as directly proportional to the heat generated. So a metal pressure vessel is there, you put your sample, you burn the sample under high pressure oxygen environment. Once it start burning, the heat is going to get released out. You have a water like tube that is going to surround your bomb or the metal pressure vessel, and then once the heat is getting generated, the water will start absorbing the heat. So the rise in the temperature of your water can be recorded outside through a thermo like sensor or a thermocouple. So that rise in the temperature is considered to be the amount of heat that is generated in the combustion chamber, because you cannot directly evaluate the heat using any instrument. So that is the reason you surround the vessel or the bomb with water, so that you can measure the change in the temperature of the water. So that can be measured using a thermocouple or any kind of other devices, because if the heat, depending upon the heat released out, thermocouple is one kind of an instrument that I am saying. So the rise in the temperature of your water is directly related to the heat generated by the combustion process. So coming back to the question, so bomb calorimeter is nothing but it's an instrument that is used to evaluate your calorific, used to measure your calorific value of a particular fuel. So here you are taking 1.2 gram of your biomass, you are burning that in bomb calorimeter, then you take the biomass and then you wash it with barium sulfate. So you will get barium chloride, so you will be getting barium sulfate, and barium sulfate is nothing but is a white precipitate. So you will be able to clearly see the barium sulfur precipitation. The weight of the barium sulfur that gets precipitated is approximately 0.35 grams. This is another information that we have. Next one is nothing but you are going to burn the sample, ammonia will be released, Jaldal method you are going to use, and then you are going to the ammonia whatever is getting released is passed through the HCl, and then the unused HCl is going to be titrated against 30 ml of 0.1 normal NaOH, and then you take then the final one is for your ash percentage. So here, since the part A says it's anhydrous CaCl2 as well as the KOH tube, there is an increase in the weight. So this means this is specifically relating to your percentage of carbon and hydrogen present in your sample. And the B part, you are going to use barium chloride. So this barium chloride and barium sulfur precipitation we saw when we were dealing with calculating the percentage of sulfur content. And then Jaldal method is used to identify your percentage of nitrogen content. So we have information to calculate carbon, hydrogen, sulfur and ash. Only the thing is what we require is oxygen. So if you subtract 100 from all of if you subtract from all of this the 100 minus all these percentages, what is going to be left over is nothing but the percentage of oxygen present in your sample. Now let's just start calculating. Here I will make a small change. This should be 1.6 and this should be 4.2. Yeah. So let's just start calculating. You can also calculate with me if you have, like if you have a pen and paper, then you can also start calculating these values with me. So first one is what we are going to see is the percentage of carbon that will be present in your biomass sample. Percentage of carbon. So if you remember the last slide, Let me move quickly to the last line. Here, so this is how you calculate your carbon that is present in the carbon dioxide, which is increasing your weight of KOH tube, x into 12 by 44. So here your x is nothing but 4.2 grams. So using that particular logic, let's just calculate this quick. 4.2 times 12 divided by 44. This will be the carbon that will be present in the carbon dioxide, which is increasing the weight of your KOH tube. So this will be nothing but, let me use my virtual calculator. If you find the answers before me, then you are welcome to tell me what will be the answer for this. So 4.2 times 12 divided by 44, 1.1454. This is your carbon present in the carbon dioxide that is increasing the weight of your KOH tube. And so what will be that in the biomass sample? So percentage carbon, because once you burn all this biomass, whatever the carbon is there, that will get converted to carbon dioxide. So this will be the total carbon that will be generated from the biomass. So you take 1.8 grams, so 1.1454 by 1.8 into multiplied by 100. Yeah, so the value will be 1.1454 times 100, 63.633%. This will be your percentage of carbon that will be present in your biomass sample. The CaCl2 is used for absorbing your water molecule. So similarly, if we calculate, and the increase in the weight of your anhydrous CaCl tube is 1.6 grams, that times 2 divided by 12, sorry 18. So the value is 1.6 times 2 0.177. So percentage of hydrogen content will be 1.8 times 100, which will be nothing but 9.8765%. 8765%. This is your percentage of carbon and hydrogen. Let's go to calculating the sulfur content. So sulfur content will be, you have 0.35 grams of barium sulfate, sulfur will be 32, the whole divided by barium sulfate's molecular weight is 233. .0480. So the percentage of sulfur will be times your biomass sample weight, that is 1.2 multiplied by 100. So that will be 4.0057%. And next is your percentage of nitrogen estimation. So for that you use your Geldal method. Do we have space? Yeah. So that is calculated as with the formula volume of the acid unused. So here we are titrating the unused acid with the NaOH. So you have to be careful with that. So the amount of unused acid will be 50 ml of zero point 0.1 normal HCl is getting used up, but it requires only 30 ml of 0.1 normal NaOH to neutralize. So 50 minus 30, that will be 20 times normality of NaOH will be 0.1, because that is what of the acid, that is 0.1 normal HCl, so that is the normality, times 1.4 the whole divided by volume of the weight of the biomass, that will be 0.5. So which will be approximately 5.6%. And then comes your ash content percentage. So that is simple. So ash percentage will be nothing but weight of the ash, that is 100 milligrams, and weight of your biomass sample, that is 2 grams. So you have to convert it into milligrams. So 2000 milligrams times 100. So that will be exactly 5%. Now you have to find out your percentage of oxygen. Oxygen percentage is nothing but, as I said, 100 minus percentage of every other elements that is present in your sample, that is percentage of carbon, hydrogen, nitrogen, sulfur, then the last one is ash. So which will be, I guess if you evaluate, it will be approximately, if you evaluate it will be approximately, just a second, it will be somewhere around 12.40%. 12.40%. You can evaluate and check. So let me just evaluate in my calculator. %, sorry, 11.85%. So this has quite high oxygen content and quite high ash percentage content. So but if you see, your percentage of carbon is 63%, and so even though your hydrogen is not going to add up to your calorific value, it's fine. 63% is quite high carbon content, but there are also other biomass sample with a much higher carbon content. So 63% on a like 63% is a fine percentage. So if you have a sample which has a higher percentage of carbon, then you have to choose that sample, or if you have something that is lower with this, then you can choose this one. So this is how you actually calculate what is the percentage of carbon, hydrogen, sulfur, nitrogen and oxygen present in your biomass sample. Then this question is something related to calculating the empirical formula. So this is very simple. If you see, I have found out what is the percentage of carbon, hydrogen and everything on a dry basis is already given to us. Here we are just asked to calculate the empirical formula for the biomass. So that's a 12th grade problem. So it's just that you need to divide all these elements by their molecular weight or atomic weight, atomic weight, and then once you do that you have to just simplify the ratios and then get them in the most simplest ratio possible. So the formula for this will be, so it's just simple, let me just write the equations alone, what you have to do. The percentage of element divided by their atomic weight. Once you do that you will be able to find out the ratios and then convert them into simpler ratios. This will give you the formula for your biomass. So here the formula is C is 1, H is 1.26, oxygen will be 0.6, nitrogen will be 0.013 and sulfur will be 0.002. So this is very simple and a 12th grade question where you just need to take the elemental percentage and then divide by their atomic weight, and once you do that you just convert them into the simpler ratios and you will be able to find out the formula. So next we come towards what is known as biomass conversion. So usually we have two different types of conversion. One is the thermal conversion and another one is the chemical conversion. In thermal conversion, it's just that you actually either burn the biomass sample either in an inert atmosphere or with a limited oxygen content or with a stoichiometric oxygen content, and then you are going to generate heat out of that process which you will be using for your other applications. Whereas in case of chemical conversion routes, you will be converting them into some kind of chemical like ethanol. You will be converting them into either a methane gas or your ethanol, which you will be using as a fuel or as a chemical in some chemical industry, or you will be using it for some energy production like electricity. Similar goes with the methane also. You will be taking out the methane gas and then use it for other purposes, as well as other purposes including the energy generation application. So here we have two different classification. So thermal conversion is, you have three different types: pyrolysis, gasification, combustion. So once you heat your biomass in an inert atmosphere, you are not going to supply any oxygen. In that case it gets converted to charcoal, oil or gas. But since this heating of the biomass takes place in an inert atmosphere without the use of oxygen, this method is called pyrolysis. And if you use limited oxygen, you call it as gasification. And if you use stoichiometric oxygen, then you call this process as combustion. So this is up with the thermal conversion routes. Coming to the chemical conversion routes, you have two different types. One is the ethanol fermentation and another one is the anaerobic digestion. So you take your biomass, you hydrolyze the biomass into simple organic compounds, and then once the simple organic compounds are formed, you convert them into your ethanol. So here there is one step missing if you see. So this simpler components of glucose is then converted to ethanol. So it will be converted to ethanol. At the end, your biomass, your target is to ferment these complex biomass compounds into ethanol so that it can be used for fuel or other kind of energy generation applications. The next one is nothing but it is called anaerobic digestion. So can you tell me what do you actually mean by aerobic and anaerobic? Like you have something so called as an aerobic digestion process. Here we use anaerobic digestion. So what is actually the difference between aerobic and anaerobic digestion? So in case of your anaerobic digestion, you have a limited or no supply of oxygen, whereas in case of your aerobic digestion, you have it actually takes place in the presence of oxygen. So presence or the absence of oxygen is something which differentiates these two processes. So here if you see the biomass, when it undergoes anaerobic digestion, it results in the generation of methane plus carbon dioxide, which together is called as the biogas will be generated. So if you even see in the lecture videos, there is a clear description of how this biomass actually gets converted to methane plus carbon dioxide. This biomass first undergoes hydrolysis because it's a very complex component. So this complex component, when it undergoes hydrolysis, it is actually break down into simple organic components. These simple organic components are then fed by the acid forming bacteria. So the acid forming bacteria are nothing but the microbes as such in general term. They feed on this simple organic components and then convert them into acid such as butyric acid or like higher fatty acids, and then it further this biomass undergoes another process called acetogenesis, where these higher fatty acids are converted into acetic acid or simpler acids. So first you take your biomass and then it undergoes hydrolysis, it forms simple organic components, then you fed this simple organic components, you feed the acid forming bacteria or acid based bacteria with this organic component. They release the higher fatty acids, and this process is known as acidogenesis. This higher fatty acids is then broken down or is then further simplified to is then further undergoes digestion, forming simpler acids such as acetic acid, and at the end this acetic acid undergoes methanogenesis process, forming methane gas. So it involves approximately 4 different processes. First is your hydrolysis, then comes your acidogenesis, where the simple compounds is converted to higher fatty acids using acid forming bacteria, and then this higher fatty acids is broken to simpler acids such as acetic acid through a process called acetogenesis, and then through methanogenesis process the acetic acid is converted to methane. So it involves totally 4 different steps for converting your biomass to methane plus carbon dioxide. So the methane that gets generated during this process has a few characteristics. They have high energy density and they have a very high upper calorific value of 39.8 megajoules per meter cube. So it's like 39.8 times 10 power 6 joules per meter cube. So that is very high and it has a high energy density. If you remember, even in our discussions on solar energy, especially the phase change materials or any kind of materials that we talked about in the solar energy, we have discussed the term called energy density. The material, whatever material we usually take or we usually use in as an energy or for energy application should have a higher energy density. So that is one of the very important characteristics for any material that you use for an energy application. So methane has a higher energy density and the upper calorific value is about 39.8 megajoules per meter cube. Then let's move to the next slide. Yeah, so biogas production. So we discussed this also about previously. If you see in the last slide, what is a biogas production? So here what happens is, it's nothing but the organic matter, as I described the process previously also. The organic matter undergoes fermentation through anaerobic digestion process using a variety of microbes, and the biogas is generated. This biogas is nothing but is a mixture of CH4 and CO2 predominantly, but apart from that, since there is also the sulfur content also present in your sample, there will be trace amount of release of hydrogen sulfide and N2 and other kind of gases, but all those things, but all those gases will be in trace amounts. Predominantly what you will be generating is the CH4 and CO2, which contains both energy from the gas, and then the digested product is used as a fertilizer. So this is one of the advantages, if you see, for the anaerobic digestion process. So what is the advantage for this anaerobic digestion process is it is not just that you are going to get energy from the gas that is released during the process, but also the digested products that is comes out of this fermentation process can be used as a fertilizers in agriculture. So this is one of the biggest advantages of anaerobic digestion process. So you get totally two advantages from one single process. You get gas, biogas, which will be used as an energy source, and then the digested product, what is generated, will be used as a fertilizer, which will be used as a manure or a fertilizer in your agricultural fields. And then now we just a minute. We now understood about what is a biogas, how a biogas is produced. So we do need to know how the construction of the biogas plant, like where this biogas is actually produced. We know the reaction mechanism, or like we know what kind of a reaction is the biomass subjected to and what we get out of this biomass, but we need to know where does this process actually occur. So for this we will be discussing about the different types of biogas plants that is present in your system. Just a minute. Yeah. So I hope like if there is any doubts that you have, then you are welcome to ask me now. So do you guys have any doubt? So it's just that we are having a recap of what was actually taught in this course for this particular week. So what we discussed previously related to the ultimate analysis was something that was extra, which is not there in the course. So it's just that I wanted to like give a complete outlook of give a complete outlook on the characterization of the biomass. Here, after that, whatever we are discussing is already there. We are just having a recap of that session, especially the most important things, so that it will be useful for solving your assignment problems. If you see, these are some of the topics. If I cover this once again, it will be useful for you in your assignment problems. So if you see your assignment problems and then this particular lecture, you will be able to have an understanding on why we are particularly discussing this topic, because these are important topics. So let's just move on and understand where does this biogas is actually produced. So it is produced in a biogas plant, obviously. So these biogas plants actually are of two different types in terms of its operation and in terms of its construction. If you see in terms of its operation, there are two different types of biogas plant. One is the batch type and another one is the continuous type. In case of the batch type, what happens is, first you feed the sample, it undergoes the digestion, the gas is released. Once after this entire process is completed, you go for the next cycle of feeding the digester with your biomass or the slurry. Whereas in case of continuous type of biogas plant, what happens is, the supply of the feed, that is the supply of the slurry to the digester, will be continuous. So your slurry will be keep coming in, the digestion process will be keep on running, and the gas, once the gas will be produced, it will be taken out. So this process occurs continuously, whereas in case if you see for a batch type, you just feed the slurry once, entire process of digestion happens, gas is left out. Here there is a continuous feed as well as the removal of the gas from your digester. So this is what is the difference between your batch type and the continuous type. In terms of its construction, we have two. One is the fixed dome biogas plant and another one is the floating dome. So what is the difference between a fixed dome and a floating dome? So in case of a fixed dome, there will be the dome which is used for collecting your biogas will be fixed, whereas in case of a floating dome, that will be not fixed. It will keep rising up and down depending upon the pressure of the biogas generated from the digestion process. So in case, so the main principle or the main difference in case of your fixed dome and the floating dome is that the fixed dome operates on constant volume principle, whereas your floating dome operates on constant pressure principle. So in case of fixed dome, the volume remains constant is because you don't have a floating provision there. So the volume of the digester is fixed, whereas in case of your floating dome, that will keep varying. So this is the major difference between both these plants depending on their construction and operation. So let's just see what is it. So if you see, this is a typical biogas plant. So if you see, even in your lecture, you will be having this kind of biogas plant. This is a fixed dome. So if you see the dome here, the point D, let me just zoom in. If you see this point D, like this dome, this arc, it is fixed. It's not like floating type as you see here. Here if you see it, this biogas collector that is present here, this dome will be floating, it will not be fixed to this digester. So that is the difference. Here it is fixed. You have a mixing tank, so your cattle dung or the biomass and then the water will be mixed here, and then it will be converted to a slurry. The slurry will then move towards your digestion chamber. So this is a mixing tank or a digestion chamber. Here your slurry will remain for approximately, depending upon the process, 30 to 60 days. Your slurry will be feeded, your slurry will be mixed with a different microorganism. The microorganism will feed on this biomass sample, digest the sample, and then the biogas will be released. Once this biogas will be released, the biogas will move up. So as the digestion process continues, the gas production will keep on happening. So as the gas production keep on happening, since it's a constant volume, it will not be able to expand. So the pressure will keep on increasing in the digester tank. So once the pressure starts increasing in the digester tank, it will start sorry. yeah, sorry. So this biogas will be generated as the fermentation process continues, as the anaerobic digestion process continues. As it keeps continuing, gas will be keep on producing. So since it's a constant volume model, volume is going to remain constant. So the biogas will keep on generating, and this will keep increasing the pressure in your digester tank. So due to this increased pressure, what happens is the slurry, the spent slurry or the digester slurry will move from this digester tank to your compensation tank. This tank is called compensation tank. Due to the increase in the pressure of the gas, there will be a displacement of the slurry from your digester tank to the compensation tank, and then it will move on to your slurry tank. The biogas that gets released here, depending upon the need, will be taken out using a gas valve. So the gas valve will be used to take the biogas from your digester tank to outside. So this is your fixed dome principle. Here your volume is going to remain constant, but your pressure is going to vary. This increase in the pressure due to the increase in the volume of the gas will cause the displacement of your slurry from this digester tank to the compensation tank, which will then get once this keeps happening, the level of the spent slurry in this compensation tank will keep increasing, and there will be overflow of the digested matter to the overflow tank, which will be collected here, and this spent slurry or digested slurry that is present in the overflow tank can be taken out and used as a manure or fertilizer in your agriculture field. One of the reason why this spent slurry is used is, as these microorganisms digest the slurry becomes enriched in nitrogen as well as the phosphor content. So that is something which is which is very useful in your agriculture field, because that will provide more nutrition to the plants and other agricultural products. So that is the reason why you need to, so that is one of the reason why the spent slurry or the digested biomass is used as a fertilizer. This is the fixed dome. So coming to the floating dome, what happens here is same principle. Here you have a mixing tank, the biomass as well as water is mixed, it passes through the inlet and then goes to your digester tank. Here in the digester tank, the biomass is fed with the microorganisms are added to the biomass, both are mixed properly. The microorganism fed on this, the microorganism feed on this biomass, and then the biogas gets generated. The spent slurry is then taken out using another outlet tube. The biogas, whatever gets generated, rises up and then it gets collected in the floating dome, and depending upon the need, the biogas gets collected using the valve. So the spent slurry again moves to the overflow tank, which can then be taken out for other agriculture purposes. So in case of your floating gas type, since the the gas holder or where your biogas is going to get collected floats, so here the pressure inside this digester tank will remain constant, whereas your volume will keep expanding and contracting depending upon the biogas generated during the process. So this is the difference. And if you see this fixed dome type plant, one of this example where this fixed dome biogas plant is actually installed is in New Delhi in India. This fixed dome type biogas plant is installed. So it is under the AFPRO Action for Food Production Program, the Dibanandu in New Delhi, India. So over there, so that is a fixed dome, Dibanandu project in New Delhi, India, which is conducted by the Action for Food Production. Over there, this fixed dome type biogas plant is installed. Can you like Satish Kumar, can you just unmute yourself? Yeah, okay. Thank you so much. So this is the fixed dome type biogas plant. So this is installed in New Delhi in India by the Action for Food Production Department. The project is called Divanandu. So what are the parameters that are affecting the biogas production, or what should be the ideal condition for the biogas production? Sorry. What should be the ideal gas for this biogas production, or at what particular condition should I put my biomass or subject my biomass so that I can get most out of it. So these are the parameters. So the pressure has to be 1.2 bar. These are the optimized parameters. The pressure inside your digester tank should be approximately 1.2 bars. The temperature for maximum conversion of your biomass to biogas should be around 35 degrees Celsius. pH should be 6.5 to 7.5. The loading rate, that is, at what rate do you load your biomass to your digester tank, should be 1 to 4 kilograms per meter cube per day. And then your hydraulic residence time, that is, what should be the time limit your biomass should be there in the digester. So it's approximately varies from 10 to 30 days. 30 days is for a non-stirred or unstirred tank reactor where there is no mixing, whereas for a stirred tank reactor the hydraulic residence time is between 10 to 20 days. So once if you use a stirrer in your digester tank, then within 10 to 20 days it's sufficient for your bacteria as well as the biomass to mix and for your bacteria to feed upon the biomass and release the biogas. And your carbon to nitrogen ratio should be around 30. And this is also a very important parameter. So why is this carbon to nitrogen ratio is very important? So the bacteria uses carbon 30 times faster than the nitrogen. So here we use two different types of bacteria. If you see the lecture, it is given, we use two different types of microorganism. One is called mesophilic and another one is called thermophilic. Mesophilic and thermophilic, these are the two microorganisms or classes of microorganisms that will be used for digesting the biomass, for the anaerobic digestion of your biomass. Mesophilic microorganisms work at a temperature of 35 to 40 degrees Celsius, whereas your thermophilic works in the temperature range of 50 degrees Celsius to 60 degrees Celsius. So this is a fact base which you should remember. So mesophilic, these are the two different microorganisms that feed on your biomass and generate the biogas. They work depending upon the temperature of your digester tank. Mesophilic is from 35 to 40 degrees Celsius and your thermophilic is from 50 to 60 degrees Celsius. So one of these interesting properties of this bacteria is that they take up carbon 30 times faster than the nitrogen. So since they take up carbon faster than nitrogen, so it becomes necessary for you to optimize the carbon to nitrogen ratio as 25 to 30 parts of carbon for 1 part of the nitrogen for maximum microbiological activity. Because if you don't maintain this, then the bacteria will not be able to do the digestion process up to a maximum extent. So if you optimize this ratio, or if you provide your biomass in this ratio of carbon to nitrogen as 25:1 or 30:1, maximum microbiological activity will take place. So maximum amount of digestion will happen. This will result in high methane content generation, because if your carbon to nitrogen content is less, bacteria will not be able to take up your biomass, so that will decrease your digestion process, the amount of biomass getting digested. So that in turn will decrease your methane content generation, or it will prolong your methane content generation. What you are supposed to get in 20 days might take 60 or 80 days. So that is something that we do not want. So your carbon to nitrogen ratio in your biomass sample should be 30:1. so that your maximum microbiological activity can take place. So here we have another one question. So I hope you can actually see the question completely right now. Here we are asked to calculate the methane content in the biogas generated from the anaerobic digestion process. So you are given biomass, but here your biomass is in terms of protein and carbohydrate content. So 125 kg of protein and 125 kg of carbohydrate is undergoing anaerobic digestion and biogas is getting generated. Here you are asked to calculate the methane content or methane that gets generated during this process, and how much, like which one generates more amount of methane, either is it the protein feedstock or the carbohydrate feedstock, and in case if one generates less, then how much amount of that particular feedstock has to be increased so that equal amounts of methane can be obtained. Also they are asking you to calculate the amount of CO2 generated during the process. This is very simple question. So let's just see. Here you have protein as well as carbohydrates. This is the given data. What they say is, for every 1 kg of your dry substance that you take, like 1 kg of your protein dry substance or 1 kg of your carbohydrate dry substance, the amount of biogas that will be generated is 700 liters in case of protein and 800 liters in case of carbohydrate, out of which in case of protein 700 liter of biogas is going to get generated for 1 kg of protein that is undergoing digestion, out of which 70% of the biogas will be your methane and only 30% is going to be carbon dioxide. Whereas in case of carbohydrate feedstock, 50% is going to get converted to, like 50% of carbon dioxide is going to get emitted. So let's just solve the problem. This is a very simple, once again a very simple problem, or I hope you guys can also tell me the answer now, since it's a very easy question. You are given with the dry substance mass 125 kg. So you have dry substance mass. Once you know dry substance mass, you can find the amount of biogas in liters. Once you know the biogas in liters, you can calculate the percentage of methane and percentage of carbon dioxide in that biogas. Let's just solve this. So for 1 kg of protein, I can extract out, or after it undergoes digestion, I get 700 liters of biogas. This is what is the given information to us. Now I have 125 kgs of protein, such a large amount of feedstock I have. So I just need to calculate what will be the biogas that gets generated during the process. So for 1 kg, if I am getting 700 liters, for 125 kg I will be getting 700 times 125 liters. So that will be approximately or exactly 87,500 liters of biogas will be generated. So 87,500 liters of biogas is going to be generated by digesting 125 kgs of protein. Out of this 87,500 liters of biogas, 70% is methane content. So 70% of this 87,500 liters of my biomass is my methane content. My methane content, or methane that gets generated by digesting my biomass in terms of liter. So the methane content will be 70% of this 87,500 liters. 61,250 liters of methane I will be generating. So the rest 30 percentage will be my carbon dioxide that gets generated. So here we are asked to estimate the CO2 also that gets generated during this process. So carbon dioxide content will be 30 percentage of 87,500. So that will be 26,250 liters. So this will be my carbon dioxide that is getting generated by the digestion process. This is for protein based feedstock. Now we are supposed to calculate it for carbohydrate based feedstock. So similarly, I guess you guys can tell me the value now. It's just you need to do the necessary multiplication and you'll be able to solve. So methane content in carbohydrate based feedstock will be what, and what will be your carbon dioxide content in your feedstock? Please let me know the answer. It's just nothing. You have to the carbohydrate feedstock's weight of the carbohydrate feedstock is 125 kg. So you just need to multiply 800 times 125, and that will be your total biogas generated. Biogas content will be 800 times 125. That is 1 lakh liter of biogas. Out of which 50-50 is for CH4 and for CO2. So it's just 0.5. So carbon content will be 50,000 liters and methane content will be again 50,000 liters. Now you are asked to compare the results which is going to generate more amount of methane. Obviously 61,250 is more than 50,000, so protein based feedstock is generating more amount of methane content compared to your carbohydrate content. Protein generates more. Protein is carbohydrates, and how much more? 61,250 minus 50,000, so that will be 11,250 liters of methane is getting generated more when the protein based feedstock is undergoing digestion. So the rest part of the question is just to add and the amount of feedstock that you will be required to generate equal amounts of methane. So suppose if you want to generate the same amount of methane, that is 61,250 liters, using carbohydrate based feedstock, what will be the amount of feedstock you will have to utilize for this much amount of methane generation? So that's just back calculation. So I am generating 61,250 liters of methane, and that is nothing but 50% of the total biogas that is getting generated. So the total biogas that will be generated will be this one, 1,22,500. This much liters of biogas. So this much liter of biogas is getting generated. So how much amount of substance I have to use? So this divided by sorry, this will be approximately, the value will be, just a second, I'm using my calculator. So 1 2 4. This much amount of carbohydrate feedstock will be required. So yes, so if you use sorry, if you so if you use 153.125 kg of carbohydrate feedstock, then you will be able to generate 61,250 liters of methane. So obviously, since more amount of the methane is getting generated with a less amount of feedstock, so protein based feedstock is better for methane generation compared to carbohydrate. Similarly, if you see, there is also another column for fat, so that we are not including in this problem. So depending, so using, if you use that data, then depending upon that you can judge which kind of feedstock will be suitable for my methane generation. So our aim should be generate more amount of methane, but at a lesser feedstock content, using a lesser feedstock content, and also generate more amount of biogas using a lesser amount of feedstock. So that should be your primary goal, or like the thought process. So with this we have reached the end of today's session. So in case if you have any doubt, then please do let me know now, or in case if you have any doubts related to the last 6 weeks of live interaction session, or live interaction session that we conducted, or in the video lectures, if you have any doubt, then you are welcome to raise your queries now. So I hope with whatever we discussed related to this week 7 live interaction session, you will be able to comfortably solve your assignments for the week 7 module. So please let me know if you have any doubts. Oh, okay, and so do let me know also, like, is everything okay with the way I'm presenting? Are you okay with that, and the pace of explanation? Do you want anything to be included, or you're welcome to share your feedback also. Okay, okay, so then in that case, if you don't have any I hope, if you don't have any doubts, if you guys don't have any doubts, then let's just conclude this session for today. Let me just stop presenting my screen. Okay, let's just conclude the session formally. So I thank everyone for joining today's week 7 live interaction session. Next week 8 live interaction session will be on 17th March, Sunday, 5 to 7 p.m., where we will be discussing or practicing more problems related to designing of the biogas plants. So in the week 8 session, you will be discussing, or you will be going through how to design a biogas plant. So we will take up with the design equations as well as problems related to designing of the biogas plant. So I also like to thank both Professor Vaibhav Vishant Gaud sir and Professor Ananda Lakshmi ma'am, as well as the NPTEL team, for providing me this opportunity to interact with you all this Sunday afternoon. So let's meet for week 8 session next Sunday. Till then, bye.